Hello and good morning to everyone to this online training of RFEM for students. I hope you started well to the day. And now I want to introduce myself. My name is Daniel. I'm responsible at Dlubal Software for the technical support and also a little bit for the marketing. I answer requests of customers, and I also create videos concerning our e-learning platform, especially for you students in order to learn your skills with RFEM better. Today we are going to do this online training, especially for you students. At my side, my colleague Praxitelis, he will help me to do this training. Praxitelis, when you want to introduce yourself.
Yes, of course. Hello, everyone. Good morning. My name is Praxitelis. I'm responsible at Dlubal for marketing and public relations. I will assist Daniel today in this training. I'm the second voice you will be hearing. I will try to answer as many questions as I can in the chat so we won't interrupt the training. So, okay, let's jump right in. Good morning and have fun.
Good, thank you for that. So, for those guys who are using GoToWebinar for the first time or who are visiting this training for the first time, just short information about the control panel of GoToWebinar. So on this panel, you have the possibility to show or hide your control panel, to adjust your audio settings, and also to ask questions. Praxitelis will answer it to you, and when he thinks it's important or it's interesting for the whole publicity, he will post this also to the whole attendees. And after every chapter, we are going to answer these questions again. So the content of this online training, first of all, I tell you something about the general principle of the FEA, so the finite element analysis. We in Germany, we are using the word finite element method, both the same. So in the English usage, we use this FEA, finite element analysis, and in Germany, we use the finite element method. So then I jump to the introduction into the program of RFEM, our structure analysis program for the calculation of different things. I will tell you it later. Then we go ahead with the introduction example. So we are going to model together a continuous plate. Yeah, and then we compare these results with a continuous beam. Then we do a stability analysis. So we check the Euler case and then a clamped frame, and then we have time to answer a lot of questions, and we have a short and little open discussion. So good. So let's jump to the basics of the finite element analysis. So first of all, the computer programs, also like RFEM, or maybe some of one knows also some other programs, normally they are based on the displacement method. Yeah, this is maybe also something you learn in your studies, the displacement method. Maybe someone of you knows also the force method, where the unknown is the force, where you have to calculate first of all the force, and then you can calculate the internal forces. Here, the FEA programs work with the displacement method. So the unknown of this equation, of this whole calculation process, is the displacement. So you calculate first of all the displacement vectors, and then you can calculate the internal forces and also the support reactions and so on. Yeah, and this analytical solution of very complex structures is in reality really hard possible. So when you want to calculate something with the hand or with Excel, yeah, you are going to the limits, because yeah, it's very hard to realize realistic results. So you have to use some FEA programs, some FEA softwares. So what going to happen there? So the real structures, they are decomposed into a mesh of finite interconnected elements. That's also the name of the finite element analysis. So the real structure is decomposed into a mesh of finite interconnected elements. We will see it later in the example. And then on each node of this FE element, the properties are described of the element continuum. And then the mechanical behavior is described by approximation sets. These approximation sets, these are the secrets of every software producer, software creator. It's very complex. And yeah, and one really important point is the discretization of each structure. The discretization describes the decomposition of a structure into finite elements. So when you are concerned with this thing, with this word, with this technical term, please consider that the discretization is a decomposition of structure into finite elements. Yeah, good. So what are the basic steps of an FE calculation? So first of all, I mesh the structure into finite elements. So I determine the local element stiffness relations at each node. Yeah, and then I have to change it to the global coordinate system. So I transform the stiffness relation at each node to a global coordinate system. And then I build the entire structure. Then I have also to consider some boundary conditions like hinges, or in this case also the supports. Yeah, do I have hinged supports, or do I have fixed supports? Do I have rigid supports, and so on? Yeah, and then I can determine the displacement vectors. So I solve the equation system, and then I have the possibility to calculate backwards to the internal forces and also to the support forces. Yeah, and this was the basic procedure of an FEA calculation. And now we are going to do this little example. So first of all, we are going to model these 3 continuous plates. And then we are going to compare these results of this bending moment with a continuous beam. Yeah, this will be very interesting, because then we can see the different results and so on. Good. So let's jump to RFEM, the program. First of all, we want to create this training very interactive. So I have prepared some questions for you. So first of all, for those who are working or visiting this online training, I want to know if you are using 2 monitors or 2 screens in order to work with this training better, because then I would adapt my pace, and that would be fine for the most of you.
Maybe we should mention that it could be that this doesn't work in full screen. So if it doesn't, just exit full screen and you should be good to go.
Yeah, sometimes there are some lags with the polls, and yeah, with the polls of GoToWebinar. So just jump to the window mode, and then it should work. Good. Now I show you the results. So most of you are just watching, I think, this online training. Yeah, 20% want to model maybe beside of this training. So I make it, you will see I make it in the right pace so that for everyone is it okay. Good. So now I want to know how good is your knowledge concerning our program RFEM, that I know, okay, which of these attendees has which experience. It would be nice to know that and to adapt my content to you. And don't hesitate to ask us questions. We are open for every questions. My colleague Praxitelis will answer you this immediately. Good. Most of you have voted, so I close this poll, show you the results. Yeah, so how good is your knowledge? Yeah, the most of you are beginners. Maybe knowledge is okay, and some of you are also very good at that. Good. So let's begin with RFEM. So first of all, RFEM. What is RFEM? RFEM is a software program for the structured analysis of plates, shells, folded plates, surfaces, and also members. Yeah. And with RFEM, you can calculate 2D or 3D structures, and you can calculate deformations, stresses, strains, internal forces, and also contact stresses. So everything is possible. You have also the possibility to calculate some volume objects and so on. So almost everything is possible to calculate with RFEM. I show you the whole user interface. I think I show you the whole user interface at the already created project. Then I jump to the creation of a new project. So for those who want to model it in at a second monitor or second screen, just watch now and see the introduction to the user interface. Then I will create a new model for you and we do it together. So first of all, when you open RFEM, you see this work window here. I open maybe this table here. Wait a moment. So now, so very above, you see the menu bar. With the menu bar, you have the possibility to have access to all functions and to all workflows of RFEM. So if you want to create something, to insert something, you can do it here by clicking the Insert tab. Just model a node, line, surfaces, and so on. Also the same at loads and load cases. You have access to the calculation settings, or also possibilities to do some options, to customize your options. So for those who are wondering why is my background white, here you can change it when you click on options and then to the configuration manager. And there you can see there is standard with white background. You can change it to the black background. So when I click here, standard with black background, double click and the background change to a black, but I prefer the white background. So double click again, and I have a white background. It's up to you how to use it. I prefer the white background. Doesn't matter. Good. And yeah, they have you several other options to do something and so on. Also some edit possibilities and so on. Yeah. Below this menu bar, you see the symbol bar. With the symbol bar, you have a faster and quicker access to the most common used functions. So if you want to create maybe now some lines or something like that, just click on that, just click on new line and draw your lines. Yeah, this is very fast forward. And by double right clicking, I finish, I end this insert, and the same also with a lot of other functions. So when I maybe want to change my view, I can click here on isometric view. I can change this view here and so on. Also maybe these views. So when I want to look against the global epsilon coordinate, I click here, view in epsilon coordinate, and I look to this side. Good. So much to the symbol bar. On the left side, you see the navigator. The navigator is very important for working with RFEM. You see all modal dotors in the data navigator. So the navigator, generally he has 4 tabs. This is a data navigator, this is a display navigator, and also the views navigator. When I show me the results of this structure here, so I show me now the results, I have also the 4th tab, the results tab. But I want to begin with the data navigator. So with the data navigator, you have all the possibilities to have an overview of data like the nodes. So when I click on one node, the node is selected, and with right click on that, I can find also this node. I see this here with the arrow, and also the same with the surfaces. So all surfaces I created before, I can click on that and I can modify them, I can edit them by just right click here and so on. Good. Also the same with load cases and loads, results, and so on. At the bottom you will find the add-on modules. Remember, RFEM is good for the calculation of internal forces, deformation, stresses, and so on. But if you want to design something, so to design maybe a steel column or to design maybe a concrete downstand beam, you have to use our add-on modules. They will give you the designs of these different materials, different areas like steel, concrete, timber structures, and RFEM is just for the calculation of deformation and stresses and so on. Good. The next step is the display navigator. The display navigator, here you can show you maybe some models or also loads or also some extra results. So in this case, I don't want to show me maybe the bearings here, so the supports. So just go here on the models, then I go to the area of nodal supports, I deactivate, and then I don't see this nodal supports. Yeah, the same with the loads. So when I don't want to see these loads here, I have here some surface loads. Just click here on loads and I deactivate the view of the loads. Yeah, and also a lot of other possibilities you have here. Maybe when you want to show you the numbering of all objects, just click here and at display navigator, go to the area of numbering here and you see the numbering of the objects. Good. Then I jump to the Views navigator. It's very helpful to work with a lot of views when your model is going to be bigger, more complex, and so on. So maybe it is for your interest to have some user-defined views. So I close, maybe I deactivate the result view, and I like this view very much. So I save this view. I can click here. Okay, create new user-defined view. I write the favorite view. And during my working process, I change maybe some views in order to work better with a program, with a model. And then I want to change, or I want to skip to my favorite view. Just click here in the Views navigator to user-defined views. Just click here, and you jump to your favorite view. Yeah. The same with the visibilities. So when you want to filter something, when you want to show you just maybe the members or to the columns, it's very easily when you do it here with the views. And now I want to show me just the columns. So I click here, members by cross sections, and I know the cross section of my columns is 300 by 300. So I click here on the rectangle 300, 300, and all columns are just shown. Yeah. When I want to add maybe this downstem beam, this IPE profile, I click on that. And the same with also the surfaces. So I click here, surfaces by thickness. I have two surfaces with a thickness of 20 centimeter. I click on that, and I can show me the surfaces. Okay, now to the fourth tab and to the last tab of the navigator. Here I can show me the results. First of all, maybe the deformation. I can show me here the deformation under global deformation, but also maybe some internal forces. So when I cancel the visibility mode that I have done before, I can show me maybe the bending moment. So I just click here on epsilon, and I see here at the downstem beam here we have a nice field moment. Or when I want to see the compression forces here with the normal forces at the columns, I see some normal forces and so on. Yeah, also the support reactions. Yeah, everything concerning the showing the results you can manage here by the results navigator. Good. Then something to the tables. Tables is acting in a similar way that like the data navigator. So when you want to create something new, you can do it here just by create a new node. The same for the lines, surfaces. So you see everything interacts with each other. So you can create a new node here in the table. You can create a new node here at the data navigator by right-clicking on node, new node, or just by clicking here in the symbol bar. So there are several ways to do an insert or an edit or a modification of a model here in RFEM. The same, you have also overview of your load cases. Sorry for that it's in German, and also node loads, or here in this case we have surface loads, so you have an overview of that. It's up to you how to use that. Good. Now I want to finish this chapter. Praxitelis, are there any questions, or do we want to add some information?
No questions yet, Daniel. Maybe we could show the controls, how you move, how you zoom, and how you select.
Yeah, thank you for that.
Mhm.
I forgot that. Thank you, Praxitelis. So, of course, the movements of our program are following. So, first of all, with the left click on your mouse, you can select, you can do a selection window, and now it depends from which side you do that. So when I go from the left to the right bottom corner, I select everything which is really in this selection window. So in this case, it would be this column here and this nodal support and also some nodes. Yeah, and I select this. When I do this from the other side, so from I begin from the right side to the left side, everything which is which is concerned in this selection window, everything within there is also going to be selected. So in this case, it would be the column and also the downstem beam and also the surface. Yeah, this is important to know the difference. So from there to there, so from left to the right bottom, I select just what is in this selection window, and from there to there, so from right to the upper left corner, I select everything which face this. Yeah, note the difference. With the mouse wheel, you can zoom in, you can zoom out. This is very important to know that. When I press this mouse wheel, I can move my work plane. Yeah, this is also important to know that. And with the right clicking, I can open this context menu. Just clicking here on the work plane, I open this context menu. When I do this with object, it opens the context menu of an object. So in this case, the member of the line. Good. And also, when I want to rotate maybe this building, just press the Control key on your keyboard and then press the mouse wheel and you can rotate it. The same functions you can do also here in the symbol bar with this icon, move, zoom, and rotate. You have the same possibilities and so on. Good. Yeah, so far to that. Now I have prepared some questions for you. So let's start with this one. I want to know of you what is a discretization. We had it before in the PowerPoint presentation. Good. Almost of you have answered, and let's show you the results. So yeah, 75% were right. Yeah, were correct. So the discretization is a decomposition of structure into finite elements, and good to know. Good. And the next question is concerning RFEM. I want to know what is RFEM, what can do that. I have to take a sip of water. Good, 90% have voted, so I close this poll window here. I show you the results. So RFEM is a 3D FEA program for calculating members, plates, walls, folder plates, shells, solids, and also contact elements. So everything is there. But not a 3D structural frame analysis program. This is RSTEP. So it's another program of our software programs. With RFEM, you can calculate members, so also a frame, so also frames, but not only, more surfaces, plates, shells, and so on. Good, keep that in mind when you work with our programs. Good. Now, I would say, let's start with the creation of our continuous plate. So, I create a new model. Just click here on New Model, or go here to the menu tab and say File, New. And after that, it opens this General Data window. And here you can insert the model name. In this case, I give the name Continuous Plate. You can make a short description. It's up to you. And I save this to my folder examples. It's up to you. You can create a new folder, so a new project, or search for the right folder here at the project manager. It's up to you. For me, it's very important to differentiate this type of models. So here you have the possibility to have different type of models. So you can create a 3D model, 2D, and different types of 2Ds. So this 2D type is especially for plates who are loaded by forces perpendicular to that. Yeah. And this 2D type is especially for walls or for 2D frames who have parallel loads, and these are plates who are acting by wind loads, for example, and these wind loads are acting parallel to the plane. Okay, so keep that in mind. For our example, it's important to choose this 2D XY, so the first one, and yeah, we don't need any of these load cases, so no classification of load cases in combination, so we don't need any standard. Maybe for the real part of working in the structural engineering, we have to choose some standards, but in this case it's not so important. But I want to have that my positive orientation of the global z-axis is downwards. Yeah. So for structure analysis, it's very common that the global z-axis is downwards because our loads are showing downwards. And this is also the reason why we have this z-axis also downwards. Good. Then I press OK. And my new work window is opened, and I can create this plate. So first of all, I go here to the symbol bar and I create new rectangular surface. I can also click here on this arrow and open the different possibilities to create a surface. I click here on rectangle, and now I choose here the material concrete C3037. For those where this concrete is not activated, you can modify, you can edit the material here just by clicking on this icon here. You can put here your material constants, your material properties by yourself, or you can open the material library and choose one of these materials from the library. So in this case, I have this concrete material. I have the normal concrete, no lightweight concrete, and I refer to the Eurocode. So for those guys who are also not from Europe, in Germany, we use this Eurocode especially, and I refer to this Eurocode, but you have also possibilities to choose some other concretes, yeah, from different standards and so on. But I refer in this example to the Eurocode. I choose this C3037. So what does it mean? We have the 3037 concrete has a characteristic cylinder compressive strength of 3 kilonewton per square centimeter, and also a cube compressive strength of 3.7 kilonewton per square centimeter. So this does mean this C3037. For those who are not from Europe, just click on OK, and I press again on OK and put there a thickness of 300 millimeters, and then I press OK. Then I click here on this first node, so on the global axis point, and then I put this plate 10 meters long. You see it here at the coordinates. Now my x coordinate is 10 meters and my epsilon coordinate is -5. I click on that, and by right clicking I end this option to insert something. Good. Now let's do I see now in the questions there is one question concerning the units. Yeah. Here at the menu tab of options, you have the possibility to change the units and decimal places. Yeah. So very interesting for those who are maybe not from Euro, or who you are using the imperial units. Here, just click on units and decimal places, and here you have the possibility to change that. So here you can change from meter to feet, to yards, inches, and so on. Adjust the decimal places, the same at loads, yeah, results, and so on. But I leave that like that because, yeah, for me it's clear and so on. But for those who want to change the units, just go here on the options, units and decimal places, and change it like you want. Good. Now to the next step. I want to create the same plate. In order to practice it a little bit more, I create here a new rectangular surface again. Now the properties are set, already set, so I create the same plate again, but in this case a little bit faster. And yeah, now I want to copy this plate from there to there. So I do a selection window and I select the whole plate within also the nodes and the lines and so on. now the whole plate, the whole surface is selected. By right-clicking, I open the context menu of this object, of these objects, because these are now more. You see, I have selected the surface, but also the 4 lines and the 4 nodes. But I want to copy everything, so I just click here, move and copy. And to copy and to move this plate, I have to enter more than 1 as a copy here. And then I choose the displacement vector, and the displacement vector is for me minus 10 meter. So the epsilon is then from there to there. I click on OK, and the whole plate was copied from there to there. Good. Now I want to move this 10 meters downwards. So I select everything again. Then I click again, right click with move and copy. And now I want not to create a number of copy. So please set it here to 0. I want to select my displacement vector, and that should be from there to there. I click on OK, and I copied it from there to there. Good. To have a good comparison to our results of our plates, I want to create also a beam, so a continuous beam. So in this case, I have to create a new single member. Yeah, create beams, downstand beams, or girders, something like that. In RFEM, is always this new single member. So just click on that and click here to create a new cross section. I create a new cross section for member start. And in order to have a good reference to the plate results, I want to create a rectangular solid cross section. So I click here on the first overview of this cross section here to the solid cross section rectangle. And I type my values of a width of 1000 millimeters and a height of 300 millimeters. The material is the same. Sorry, the material is here the same. Just click OK. I apply this again with OK and press this also again with OK. Then I model this continuous beam from that step here, from that node to that grid point, and close this insert also with escape or with the right click on your mouse. Good. Next step is that we divide these lines in order to have lines to create line supports here. Now, I change maybe a little bit my view. We want to create a continuous beam here. Yeah. So we need an additional node here to create our support here, and also additional lines in order to create our line supports here. So we have to do that now. So I change my view again to the front view. So I click here on view in Z direction, and I look again to this side to have this view. So what can I do? I can divide lines in order to have an additional node of this line. So I click here on the bottom line here of this plate, of this surface, right click on that, and then I can divide the line graphically by n intermediate nodes or by distance. In this case, it doesn't matter what to use. everything is possible, but I want to show you the different options. So first of all, we do it graphically. So here, first of all, on this window, you have this division spacing and also the steps how you divide this. So when you go along this line, you see maybe the different numbers, yeah, and I want to divide this except at the middle of this line, so I need the number 5. So I divided this, and now I have an additional node. Now I have this reference node that I can create a new line from there to there. So let's do that. Again, here in the symbol bar, click here on new line. And now click here from this node to this node. Good. By double escape clicking or double right clicking, I close this entry. We do the same again with this line. So right click on that line. I divide the line, but in this case in intermediate nodes. And now it's very important to know these arrows. Yeah, these arrows symbol me the orientation of the line. So every line, every member have one node at the beginning and one node at the end. And this arrow shows me the orientation. So in this case, this arrow shows from the left side to the right side. So this means that the line has at the left side his beginning node, so his starting node, and on the right side his ending node. So, and when I want to divide this in intermediate nodes, and I have the 1, it divided me at the half of this line. When I put that 2, I have this. I have 3 lines, so 2 additional nodes, and so on. I put the 1, and it was cutted exactly at the half of this line. I create a new line again, and I create this line from there to there. Good. Now, very important workflow in RFEM is copy something per or via drag and drop. This is very important to know. It's one of my best tips to you to know that. Just click on one of these lines, and now with the pressed Ctrl key and the pressed left mouse click, you can easily drag and drop something. Yeah. And when you want to leave it, just leave the left mouse wheel, left mouse click. Yeah. So again, I make this, I undo this. So with the keyboard combination, Control key and Z, I can undo some things, and I want to do this drag and drop function again. So left click on this line, then press the Control key and press also the left mouse click and leave that here. This is a very important workflow and function of RFEM. Good. Now we want to divide here this beam also. So I click here on this beam, right click on divide member. So keep it in mind, a member is also a beam or a column or something like that. Now I want to divide it by distance. Now I have again this orientation of this beam, the same again. So on the left side, I have the beginning node, and on the right side, I have the ending node, because my arrow shows me from left to right. And I want to have the division here at 5 meters. I click OK, and that was it. Good. Now I want to create the nodal supports and the line supports. So first of all, the line supports, because we want to have here a continuous plate of these surfaces. So we need new line supports. So just click here in the symbol bar, new line support, and we choose this hinged support, because when we are going to watch this supports, we can do that here, create new type of line support. We see, okay, the UZ, so the support in UZ is activated. What does it mean? So when I activate some of these things here, so restraints and supports, I block the deformation, I block the displacement or the restraints. So I want to have that my support is carrying vertical forces, so I have to block the displacement in the Z direction, and this is also the reason why there are going to be vertical forces. I press OK. Now you can choose the hinged or the global. It's the same. You see it here at the arrows. Click OK, and now click on these lines here. Yeah. The same at the beam. But in this way, I do it a little bit another way. So I select first of all this beam here, this part of beam, because I want also to create here at these nodes this nodal support. Now I go to the symbol bar and click on new nodal support. And here in this case, I choose again the hinged nodal support, click OK, and you see here the nodal supports. And for that point, for that node, we need a different nodal support, because at the moment it can be possible that the beam has torsion, and that he can rotate along his own axis, and this is something we don't want to have. So I have to create a different nodal support. So here again, new nodal support. I click here on create new type of nodal support, and I have to activate this phi x, yeah, in order to block the rotation about his own axis. Yeah, this is very important. Click on OK, again on OK, and we have this. Good. So much to the modeling of supports and plates. Now we are going to put the loads. one important point. In order to put the loads, to add the loads, it's important to have at first your load case, because every loads are referred to two load cases. Yeah. So in this case, we have to create first of all our new load case. So here at the symbol bar, just click here on new load case. And here it doesn't matter if we have some description, so I write here test load case. But what's for me very important is that I don't consider the self-weight, because I want to have clear results. So I deactivate it. Yeah, of course, in reality, when you do real structural engineering stuff or real structural analysis, you have to consider the self-weight, of course. But in this case, I just want you to show the different results. And that's the reason why I deactivate the self-weight. I click on OK. Now I can put the loads on the surfaces and plates. So here I put the new surface load. It opens a new window, and I have the load type force, and the load distribution should be uniform, not linear, uniform, constant. And because we are working in the 2D work plane, so we have a 2D object, 2D type, the load direction are only possible in the global Z direction. Yeah, and we have a magnitude of 10 kilonewton per square meter. Again on OK, and I choose the surfaces here. Good. Now I have to create it here also for the beam, so for the member. Keep that in mind. We have in RFEM two possibilities of line or distributed loads. First of all, the member load and the line load. Because we have here a member, yeah, it's very important to use really for that the member load. The line load is for the lines of a surface, like wind loads of edges. So when you want to put loads on edges of surfaces or of plates, of shells, you have to use line loads. But if you have really members with cross sections and so on, you have to use member loads. So keep that in mind, please. I click here on new member load, put here also the same load parameter, 10 kilonewton per meter, and click on OK. Good. So far to the insert of loads. Praxitelis, I see some questions.
Yes,
should we answer something? Should we do something again?
We had several questions about the stiffness of the stiffness and the type of the plates. Maybe you could explain it in a minute. For example, could you explain about stiffness type of plate?
Okay, of course. We have different stiffnesses type of plates. When I right click on one of this surface here and I click on edit surface, you see here on the right side the surface type. Yeah. First of all, the geometry. In this case, we have a plane. So a plane is really when you have something in one plane. And the stiffness, we have here different stiffness type. First of all, also we have the possibility to have maybe an orthotropic stiffness. So here at the bitmap, you can see different types of that. And when you click on the right icon here, you can edit the parameters of stiffness. And then you see also the stiffness matrix, and you can modify that. Yeah. And there are so much possibilities to do that. Yeah. So when you want to have the constant thickness or some effective thicknesses, you can modify these stiffness factors, yeah, or the stiffness elements, sorry, not factors, elements, yeah. And then you see it here also in the material properties, and then here at the stiffness matrix. And this was what I told before at the beginning of our PowerPoint presentation. At each node, this different type of stiffness matrix is we are considering for the calculation. Yeah. So when you want to modify that, you can do it by your own way. That's possible. Then we have also the possibility to have glass stiffness. There you have to use an additional program, RF glass, because it's also a different stiffness type of plates. Also laminate, so when you want to do some timber structures, especially cross-laminated timber, very famous, you can do that here by creating also new stiffnesses. It's similar, so here you have also to use an additional add-on module of our software, and with the help of the add-on module, he will calculate the stiffness matrix of that. You will see it then later. And you can do it also rigid. So without no deformation, infinite stiffness. Yeah. But in this case, we leave it at standard. Good. Another question?
We get several questions. I would recommend the less relevant ones to do in the end, so we can manage to complete the training. I've got one more that we could answer now, and it is there are two options for dividing members. One saying it will create a node without dividing a member. When is it useful to use this option?
Okay, I have to recap this. Okay, without dividing member. When I divide some objects, or in this case, this member here, I would recommend you to divide it every time in different member parts. Because when you have here a node without division of these members, the node isn't going to be considered by the program. I can show you it. I can show it to you. I do something new. You don't have to do this. I just want to show it to you. So look, I create two lines. I create two lines, yeah, and they are acting independent from each other, yeah. So these lines is for his alone and this line is for his alone. Yeah. And when I want that they have one point here, one node, so that they are acting with each other, I can create an additional node here at the symbol bar by connect lines or members. I draw one selection window and here a new node was created. And now you can also see this line is acting with this line. And this is very important because when you want maybe to calculate members, yeah, so you have members and you don't want that they act on each other. You have to model it like that in that way, yeah, to have no additional node here. I hope this question was answered.
I believe we should carry on and maybe answer that the remaining questions at the end.
Okay, for those who are entering this session now, no problem. We are recording this and we will send you then the recording and also the whole models. So no worries. Okay, good. Now I jump back to the continuous plate. We have inserted the loads. Now let's do the different FE mesh refinements, because I want to have at each plate a different FE mesh refinement. Here I want to have the size of an FE mesh by 1 meter, 0.5 meter and 0.1 meter, because I want to show you the different results depending on the different FE mesh refinements, different FE mesh size, because this is a very important point to know that. Yeah, so let's do that. So first of all, just click here on the surface. By right click on that surface, you can do here a FE mesh refinement. Yeah, click here on new, and here you have the possibility to create a new FE mesh refinement. And because we do this FE mesh refinement at the surface, the surface is just selected. So we apply to the surface and we put here a length of 1 meter. Just click OK and click on OK again. And you see here this square. It symbolizes me that here we have a FE mesh refinement of 1 by 1 meter. Yeah, the same we can do for the second surface. Here again, FE mesh refinement. Go again to new, create a new FE mesh refinement, and here we put a value of 0.5 meter. Click on OK. And now I told you also that you can do the same creation of model objects and so on also with the help of the data navigator. I want to do that, so I jump to the data navigator, go to the area of FE mesh refinements, and when I open this structure here, I see the already created different FE mesh refinements. I want to create a new one. I click here on with right click to new FE mesh refinement, and I refer first of all to a surface. I click here this surface, so the third surface, and then a target FE length of 1.0 meter. Good. In order to see the results better, it's good to have a comparison of the internal forces of that beam and also of the internal forces of the plates. So in order to handle this better, we have to create sections. Yeah. Also here at the data navigator, I can create sections very easily by right click on a section. You find it here. Just create a new section. Give them a name and set the different points of sections. I refer just for on the one surface. So here on surface number 1. And the edge points of my sections are the middle lines of the outer lines of this plane here. Okay. The section on surface, the projection direction is in global Z. I press OK, and I make this again for the next surfaces. So again, here on sections, create a new section. The section name is 2 minus 2. The edge points of the sections should be from there to there. And my surface number is the second one. Click on OK. And again, create a new section, 3 minus 3. Choose the right points and also the right surface. And then click on OK. Good. Now everything is ready for the calculation. So we can calculate it, and this is what we are going to do now. So just click here on the menu bar, calculate, and you can calculate everything, or when you have different load cases and when you want to show you one special load case, you can click here on to calculate, and then you can choose this load case here, or just click here in the symbol bar, calculate all. Yeah, so I click here in the symbol bar, calculate all. Yeah, and the program is calculating, and this is what you are going to see now. Good. So first of all, you see the global deformation. But this is something what's not so interesting. Yeah, you can watch maybe the deformation in some way, but more interesting are the internal forces of the member here, and also the internal forces of the plates. So I activate it. I click here on surfaces. Now I see the basic internal forces mx. Mx means every surface has a local axis system. By right clicking, I can show me also the local axis system of the surface. So right click on the surface here at local axis system on off, I can show me the local system. And the basic internal force of mx says me that these bending moments, these internal forces, are along the local x-axis. Yeah, and this is, I think, very clear because we have here field moments, here negative moments, like here at the beam. So in order to see the results better, I activate the sections. Now I see the different results. Yeah. Good. Now you can maybe see also the different the different results of the sections, yeah, and also the different sizes of the FE mesh, because here we have 1.1 meter, so at every 1 meter there is a result, and here 0.5 meter and here 0.1 meter. And what I want to show you is that it depends which FE sizes you have, because it can cause different results. Good. One important point is also at the when you go there to the calculate and also to the calculation parameters, that you have here the possibility to activate shear stiffness of members. Yeah, so especially in the study when you want to calculate something by hand, so you have maybe a continuous beam with the help of the force method, or also with the help of the displacement method, you can calculate your internal forces. And when you want to compare your results with the results of RFEM, it's very important to keep in mind that RFEM is always calculating with shear stiffnesses of members. That's the standard. And this is maybe also the reason why you don't get the same results like in RFEM when you compare your beam results with the beam results of RFEM. When I deactivate this, I click on that, click on OK again. And I calculate this thing again. You see the internal forces, so the bending moments especially, changed here. Because in the study, you calculate your beams, your girders, with an endless rigid shear stiffness. So the shear stiffnesses are endless, so it's rigid, the shear stiffness. And in reality, you have some shear stiffnesses to consider, so some shear deformations. And due to the consideration of additional shear forces, it will be there some different results. Yeah, so keep that in mind when you calculate by hand something with the help of some books or something like that, and you want to compare it with RFEM. Please keep that in mind. Please consider that here in the calculation parameters you have to deactivate or activate the shear stiffness of members. Yeah? Good. Praxitelis. Now we have a little bit time for answering some questions.
Okay, Daniel. We got one right now. Is it possible to analyze design precast concrete slab single span with steel beam and column? It is the last one if you want to read it again.
Yeah, is it possible to precast to design precast? Wait a moment. That's there. Okay. Okay. Yeah, it's possible to design reinforced concrete members or surfaces, but I don't know how to consider different settings, different properties of precast members. So for sure, it's possible to calculate reinforcement concrete surfaces, plates, or objects, models, yeah. But when you have some I have to look it up, the word in in English, sorry for that. Pre-stressed concrete, then it would be a little bit difficult because there are a lot of precast concrete slabs with pre-stressed concrete, and this is not possible to do that. We had some time ago a program who could do that. His name was RFEM, but we doesn't support that anymore. But normal reinforced concrete, it's possible to calculate. I don't know what is CFST concrete. I have to look it up.
Maybe I can look it up and you could continue.
Yeah, you can look it up and maybe you will find also something.
We'll do it. Okay, we got one more question about the division of members, because the question was about the menu that shows up if you click, for example, divide member, and then on divide member in n intermediate nodes. In the new menu that pops up, that is there is an option to click on divide line by new intermediate nodes or place new nodes on the line without dividing it.
Okay, I understand. We can look it up. Again, here I go to my test model here. I create here also new lines. Yeah. And you want to divide this line here by divide line and then n intermediate nodes. And then I think you meant this,
Exactly.
this method, place new nodes on the line without dividing it. Yeah, this is also possible. Like I said before, you can create here new nodes, yeah, but then the node doesn't have any behavior on the line. So it works alone, yeah. It doesn't have any influence on that line. We can do that, yeah. So when I divide this node here in one intermediate node, so we get here in the middle of this line a new node, but then look it up, okay, this line wasn't divided, yeah. And when I create a new node from there to there, these lines wouldn't act on each other, yeah. It's the same when I would go through here, yeah. So when I would have here some cross sections or real members, and I would put there some loads, they wouldn't have an impact on each other. Yeah, this is something you have to know. Of course, you will get the recording of this session here.
Okay, should we continue with the training or do you want to answer more questions?
maybe one more question.
Okay. Someone is saying, could you talk about connection in the nodes when 3 members are connected? Sometimes RFEM warns about instability.
I understand. Okay, I think this can be possible when you have maybe hinges. I explain it to you here, this example. I create now very fast some cross sections, some IPE profiles. Okay, so look, here we have very small, this thing. I make it a little bit bigger. Good. So I make a one continuous beam. So I divide this again here, maybe a little bit by distance. So here in the middle. And make also some sliding supports, nodal supports. And now I want to have here a hinge. So I have to divide it again. I create here a hinge. So in this case, in RFEM, is it so that we have to create member hinges? So we have to create member hinges. So I go to this beam here, edit member, and I create a member hinge, normal moment hinge. So in this case, I set the rotational release MY, and I create here a hinge. So now the whole beam is statically determined. And when you would have here an additional hinge, like here again, so I make this here, then it would be unstable, yeah, because you have here a hinge chain, because we have here 2 hinges, and then it would be unstable. So keep that in mind when you have 2 parts of members. It's okay to have just one hinge. It's okay to just one hinge in order to consider the 0 moment here. 2 hinges would cause a hinge chain. And when you have 3, when you would have 3 members, so I model one member again, and when you want to have here also an hinged joint, yeah, just click here on the upper member, create here a new hinge, and then you have the hinged joint. But if you would do here an additional joint, an additional hinge at this beam here, then you would have again an hinge chain, yeah? So the same amount of hinges, like the amount of members, would cause an hinge chain. Okay? I hope that the question was answered. Due to the hinges, exactly. Yeah. Exactly. Yeah. So you have to consider it in the right way. And also, when you create hinges at the nodal supports, this is also false. This is not correct, because the nodal supports at the end or at the beginning there are hinges. Yeah, keep that in mind. Good. Then I would say let's move forward. Praxitelis, some additional things, or maybe?
I think we can carry on.
Okay, good. Okay, so much to the continuous plate in comparison to the comparison of the beam. Now I have prepared a test for you. So what happens if the shear stiffness is activated? Please answer that. Good. Maybe I will wait for some more answers. Just 60% have voted. Okay, good. I close this poll. And the right answer is the first one. So shear deformations are considered when the shear stiffness is activated. So I get additional deformation because we activate also shear forces due to the activation of the shear stiffness. Good. So much to them. Now, again, to the a little bit theoretical part. I jump back to my PowerPoint. And now I want to tell you something about the plate theory. Yeah, very important in my opinion. So I don't know how you learned this in the study, but I learned this in that way. So we have two theories of beam calculations. On the one side, we have this Bernoulli beam, and on the other side, we have this Timoshenko beam. So what are the what does the Bernoulli beam say to me? So in this case, the cross section remain in plane, yeah, and also the cross sections remain perpendicular to the member axis. And we assume, so these are the assumptions of Bernoulli. And what's very important, like I said before, with the shear stiffness and so on, Bernoulli doesn't consider shear deformations. So we have rigid shear stiffnesses. That's also the reason what you learn at first, also in my opinion, what you learn at first in the study, when you calculate beams and girders and so on, you don't consider the shear deformations at first. Yeah, because a lot of books say to use some general formula in order to calculate this continuous beams a little bit faster and so on. And yeah, and this is also the reason why we don't consider that. And on the other side, we have this Timoshenko beam. And the Timoshenko assume at first the same positions like here. So also the cross section remains in plane, and also the other cross sections remain perpendicular to the member axis. But the Timoshenko consider the shear deformations. So the shear stiffness is limited, it's not endless, it isn't rigid. So when I show it to you, maybe in a graphic, in the image, here we can see the perpendicular. So after the deformation, we see here that the deformation is perpendicular to the member axis. And the Timoshenko, there we have an additional angle, so additional deformations due to the activation of the shear deformations or the shear stiffness, because we consider the shear stiffness here at the Timoshenko beam. And these two theories we can refer to the plate theories, to the plate elements. So the same thing of Bernoulli is here in this case the Kirchhoff theory, and same of Timoshenko is the Reisner-Mindlin theory. So what are here the assumptions? We have here, first of all, geometrical linear. So we are considering just small deformations. We use the Hooke's law, and also the cross sections remain flat, so in plane, and we have no warping, and also a constant thickness. But the most important point is that we don't consider any shear deformations. And in comparison to the Reisner-Mindlin, we consider shear deformation, and we consider also additional strains of transverse or lateral strains. In order to show you what are transverse and lateral strains, I have prepared one picture here. So when I have one beam here and I pull it along his side, along his length, so I have here some tension forces, the cross section of this beam becomes in the width smaller due to this transverse lateral strain. And this factor mu is this consideration of this transverse or lateral strain. Okay, good. To summarize it, I have on the right side Kirchhoff, and on the on the left side Kirchhoff, and on the right side Reisner-Mindlin. To say it again, we have no consideration of shear deformations at Kirchhoff and consideration of shear deformations at Reisner-Mindlin. So how to use this in the practice? Kirchhoff supports good results when I have thin plates, so when I have really normal slabs in the concrete calculations of the buildings, so 20 up to 30 centimeters, there are the results okay. But you have to consider that there are just pure bending load bearing capacities. So no consideration of shear forces, and the calculation is also just a simplified approach. When I look to the Reisner-Mindlin theory, the theory can use for thick plates, but also for thin plates. Please keep that in mind, that you also get very good results when you use the Reisner-Mindlin for thick and thin plates. Because the component of the shear influence is relatively high, and if we would neglect the shear forces, the results wouldn't be good, and also the errors would be too high. And in addition, we have also higher value approach, and because we are considering the shear deformations, we have also more accurate shear forces. So to summarize it up, in my opinion, it's better to use always the Reisner and Bindlin theory. But it's also good to know, okay, there's also the other theory like Kirchhoff, and it's important to know the differences between them. Okay, good. Now I show you also in the program. When I jump here to the model again, and I go here to calculate and to the calculation parameters, I have here the possibility to choose one of these plate bending theories. And in this case, the standard of RFEM is always Mindlin. So maybe you remember these results here. I changed to the Kirchhoff method, to the Kirchhoff theory. I calculate everything again. And you see maybe the different results of the internal forces here, of the bending moments. Yeah, they're a little bit different. So keep that in mind. If I would make this surface bigger, so with a greater thickness of this plate, the results would be more different. Okay, good. So much to the plate theory. Praxitelis, are there any questions concerning this chapter?
Just give me a sec because I was answering questions.
Okay, sorry for that.
No problem. Okay, someone is asking, is there an error showing any locking happening in case of occurrence? I don't quite understand the question.
Me either. Sorry for that. Maybe I can answer the next question. Are we conservative by considering a bigger or smaller FE mesh? It's up to you. How big is your model? And it depends on several things. First of all, when you have a really big model, it's up to you how you want to do the FE mesh sizes, because the smaller the FE meshes are, the slower or the longer your calculation needs. But the more exact or more, not better, but I have to look it up, this word. Sorry for that. Yeah, the more exact results you get. Yeah. And maybe you see it here again. You have here 3 different plates with 3 different FE mesh sizes. And you see the difference between those results are not so big. So to calculate with a greater FE mesh could be maybe a good approximation to the right, to the exact result of this beam here. So it's up to you how to discretize, how to do your FE mesh sizes. Okay, what are the 4 different things? I mean, what is the difference in the 4 things? So here in the surfaces we create. Okay, I tell you the difference. So the difference is that we create 3 different types of FE mesh sizes, so of FE mesh refinements, and I wanted to show you the different results in comparison to this beam result here, to this member result here. because when you calculate beams and members, the results are mostly exact, yeah, because it's easier to handle, to consider that in the stiffness matrix. But if you calculate surfaces, plates, shells, there will be every time an approximation to the right results. There will be never the exact solution. Please keep that in mind. And I wanted to show you the different results depending on the different sizes of the FE mesh. Okay.
Okay. Then we have the question, how can we have an aspect ratio for mesh size different than 1?
This is here possible when you calculate, when you go to the calculate and FE mesh settings. Here you can take more options, more settings to edit your FE mesh settings. First of all, when I wouldn't do the manual FE mesh settings here, so the FE mesh sizes here, the program set the general target length of finite elements to 0.5 meters. Yeah, and concerning the ratio of FE rectangle diagonals, you can do it here by delta D. You can adapt, you can edit this here, you can modify this here. And when you want to say, okay, I just want to use here maybe also triangles only, yeah, you can change it here. Please, here you can do that.
Okay.
Good. Good.
Should we continue with questions, or do you want to carry on with the training?
I would carry on with the training.
Okay. Maybe we should let everyone know that no questions will be left unanswered. We will answer every question via email if we don't have the time to do it today. So don't worry.
Okay, good. So now I prepared for you again a small test. Exactly. So the whole recording and also these models which I modeled, you will get via email. Just click on the window. It can be possible that some of you can't answer this because you are using the full screen mode of this GoToWebinar tool. Just use the window mode, then it should be possible to answer or to choose the answer. Good. So let's wait maybe 10 seconds more. Good. I close this poll window and I show you the results. So 77% of you have chosen the right answer. So yeah, the plate theory of Kirchhoff considers no shear deformation. That's right. Good. Now I jump back to my nice PowerPoint presentation. Now we are going to do this Euler case 1. Yeah, so we look to the stability analysis of this clamped column, and then also to this frame here. Good. So I create a new model. I enter the name Euler case 1, and now it's very important to do this, to have a type of model in 3D, because we want to look both sides of buckling. Yeah, so we are looking both eigenforms in both directions, and so this is why I do that here. So again, I want to create one member. Keep in mind, in RFEM, it's also possible to create members and beams, columns, and so on. So I click here on New Single Member. I click here on Create New Cross-Section for Member Start. And I choose this one, this HEB profile. For those who can see them, you can just click here on Import Cross-Section from Library. And here you have the possibility of a lot of different cross-sections. I choose here the I sections. And now you have here the possibility to choose the right manufacturer and maybe also some different cross-section shapes. But I leave it as normal. So I choose here the HEB. In Europe, it's very it's very usual, this profile. I choose this HEB 300 profile, click on OK. Then I click on again on OK, and I apply this again with OK. And now, keep in mind, when you use the model type 3D, you will have different work planes. In this case, I have the work plane X, Y, yeah. And in this case, I can just model it in this work plane. Yeah, so when I want to create here maybe some beams, it's not possible to do that into the height. So I delete this again. There are two possibilities to do that. First of all, to change the work plane, that I can model it, my beam upwards. Yeah. Then I have this beam here. Or when I do this, when I delete this again, and I leave this as this work plane, I have the possibility to create my member perpendicular to work plane. And in this case, it should be 10 meters high. So I put there a value of 10 meters. And you see maybe also the member here, the column, but in the wrong direction. I want to have it in this direction. And I put it like that. And I have my beam here. Good. Now, next step is to put there some supports. I want this as a clamped node here, clamped bearing. So I create here a new nodal support. First of all, I select this node here. Then I click on new nodal support. And then I say rigid. So every deformations and every restraints are considered. Click on OK. Yeah. And this is my Euler column number 1. Then I need additional node loads. So I have to create, first of all, a new load case. To do that, I click here on the symbol bar on new load case and click here on test. Yeah, it doesn't matter what's the description of this load case is, but I deactivate again the self-weight because I just want to have clear internal forces. Click on OK. Then I create this new nodal load. And now I want to have a compression force of 100 kilonewton and also a horizontal load of 20 kilonewton. Here you can refer to the directions of the nodal loads, also here with the help of this bitmap and also with the help of this global coordinate system. Click on OK. Select this node here and you see the different nodal loads. So now I want to show you a really important thing. So I changed a little bit my view, so in the reverse Y direction, and I calculate now. I click here on calculate all. And now you can see here the different internal forces. So of course the bending moment is here minus 200 kilonewton meter. I think that's clear. Also the compression force of 100 and also the shear forces. So, but when you look to the deformation, so to the deformation in the global X direction, it's 127 millimeters. So, and now I want to show you one important thing. The calculation after the first order, theory first order, and the calculation after the second order or the P delta. Yeah, what really important thing. So I open the load cases and combinations, and I want to show you the differences concerning these two calculations method of analysis. Yeah, so generally the load cases are analyzed or are calculated by a geometrical linear analysis, but load combinations, for example, by the second order analysis. Maybe you know that also under the name P delta, yeah. And I want to show you the differences between these two methods, yeah. Okay. The second order analysis, when I choose that and I calculate that, it will make the equation, the equilibrium of an undeformed system. First of all, we had the first order, yeah, the geometrical linear analysis. There we make the equilibrium of the whole structure at the undeformed system. And there the P delta method said to me that we make this equilibrium of the whole structure at an undeformed system. No, sorry, at a deformed system. Sorry. The first order say we make the equilibrium of an undeformed system, and the second order, or the p delta, says to me that we make this calculation on a deformed system. Yeah, sorry for that. Okay, now look to the deformation in the horizontal x direction. This is 137 millimeters. And now look to the bending moment. And there we get additional bending moment of 13 kilonewton meters. And when you ask where comes these additional 13 kilonewton meters, this is due to the calculation of the second order, or the p delta method, because this 100 kilonewton multiplied by the deformation, by the horizontal deformation of 137 millimeters, equals to the delta of 13 kilonewton meter plus this normal bending moment of the 20 kilonewton meter multiplied by the length, is this whole bending moment of 213.74 kilonewton meters. Yeah, so keep that in mind, that you have different results when you are considering two different methods of analysis. Okay, so far. For those who are asking if you're doing a column or beam, in RFEM there are members, and members can be beams and columns and girders, doesn't matter. But the loads, how they react on one of these members, says you, okay, is this a column or is this a beam? In this case, we have a column, because we have this normal compression forces, and normally it stands for a column. But
Daniel, maybe you could double click on it so everyone can see the member types.
Okay. Yeah, when I double click on that, you see here the member types. And normally you have here as a standard the beam type. Yeah, so the beam types transfer all internal forces, like the bending moment, like the shear forces, and also the normal forces. And this is what we want to have there when you just want to transfer, I don't know, just transfer tension forces or compression forces. You have to choose one of these member types. And when you want to have at the ends hinges, so that you don't transfer bending moments on the other member or the other members, you have to choose this truss type. Good. Now I want to go ahead in order to show you the stability analysis. So I change this nodal load. I leave just the normal compression force of 100 kilonewton. I delete this horizontal force. And I activate here on the left side at the add-on module here the RF stability. For you students, when you use the student version, you have access to all add-on modules of our software. So I open this here. And now it opens a new window. What does RF stability do? The stability analysis calculate by the help of the eigenvalue method the different eigenforms and also the different eigenvalues. Yeah, you know, maybe the Euler. Euler was one mathematician. He calculates different cases and say, okay, this is my critical load factor, this is my critical load, and these are my critical lengths, and this is something what area stability does in the similar way. So in order to get the different eigenforms, so the different buckling cases, I deactivate here the minimum initial pre-stress of cables and membranes. We don't have that, and also deactivate this. But now, very important that we activate the division for straight members, because every member is also divided internally by RFEM, and there we have to set the minimum number of member division from 2 to 10. This is very important to do that. Click on OK. And then let's calculate this thing. And we get, first of all, a critical load factor and a magnification factor. What does say the critical load factor for me? This is the factor you have to multiply the load in order to get an unstable system of your model. So when I multiply this factor of 4.4 with 100 kilonewton, so I get a nodal load of 440 kilonewton, my system is going to be unstable. So there will be an error in the calculation of RFEM because the system is unstable. When I do this when I consider this method in the theory of second order, or the P delta, yeah. I have here also my effective length. So here the critical load. So you see the critical load composed of this critical load factor. So if my column or my member gets a normal force of more than 443 kilonewton, the system will become unstable. So we do that. Now I want to show you maybe the different eigenvectors. I show me maybe this eigenvector, eigenform a little bit better. So I go to the display navigator. I click here on deformation, members, and show me the cross-section colored. And now you see the first buckling case, the first buckling form of this column here. And when we zoom a little bit in, you will see, okay, I think that's very clear. We have our Euler case 1, so the buckling form, the eigenform looks a little bit like that. I think that's clear. And the first case when this system will become unstable is that the column buckles around his around his weak axis. Yeah, when I show me the local axis of this member, I see, okay, here I have this y axis, and here I have this z axis and the local x axis. The weak axis, or the weak cross-section properties, are the moment of inertia of the weak moment of inertia of this column is around his weak axis, so around his local z-axis, and this is also the reason why the buckle, why the column buckles first of all around his weak axis and around his z-axis. So, and when I change the eigenvector number, so to 2, this is around his strong axis, yeah? And these are maybe the cases you know also from the study. And this is very important to know that. Good. Let's jump again back to the area of stability. And let's look maybe again to the effective lengths. And you see the effective length, the factor, here is it 2 and here 2006. And when you ask, or when you're wondering why isn't it exactly 2, because Euler said, okay, we have the effective length factor is 2, so we multiplied the first length of this column here by this factor, and then we get the effective length, so the critical length of this. And when you ask yourself, why is it exact 2? This is because we considered again the shear deformations. So the shear stiffness. When I go back to these options, when I go back to this calculation parameters here, and I don't consider the shear stiffness of members, and I calculate everything again, I get the exact effective length factors. So I jump back to this area of stability, and you see the effective length factor are 2, and also the effective length. Good. So much to the stability analysis of the Euler case 1. Now I want to show you what happens when you get a critical load of more than 443. So we have here this nodal load of 100 kilonewton, and when I put there a value of 444 kilonewton, and I calculate it with the method by P delta, so I consider the second order analysis, you will see that my system will be unstable. I calculate it. Yeah, and you will get this arrow, this calculation arrow, and there you have this description of the arrow, so that the stiffness matrix is singular, the model is unstable, and so on. Because we have a normal force of more than 443 kilonewton, because our nodal load is higher than the critical load. And this is one thing I give you as a hint. Yeah, please consider that. Okay, good. Praxitelis, are there some questions?
Yeah, there are some questions indeed. Someone is asking, what about torsion lateral torsional buckling in the section?
Yeah, of course, you can consider it with this program. You can calculate also torsion, but in this case, we don't have any torsion, but the programs consider torsions. That's clear. Yeah, of course. Because we have also our load at the, I don't know, Praxitelis, do you know the English word for Schubmittelpunkt?
Torsion middle point, maybe.
I have to look it up.
Shear, don't know.
Center of thrust. Yeah. I'm sorry for that because I have to look one English word. Maybe I find it there.
Someone is saying inflection point in the chat. Center of gravity.
Inflection point. Center of gravity, that could be possible, yeah. Okay. So because the loads, if I have some nodal load like here, it acts on the center of gravity or inflection point of the cross section. Yeah. And this is also the reason why we don't have any torsion. Okay. So normally the so in RFEM, the loads are acting on the center of gravity or inflection points of these cross sections. Okay, other questions?
Okay. Just give me a sec. Is it possible to do calculations in RFEM based on Saint-Venant's principle of elasticity? It's at 11:15.
11:15. At which time?
Exactly.
Okay,
Yeah.
Yeah, you can consider it in some way, but I think this is more when you design a cross section. Yeah, and when you want to do a design of this steel column or steel cross sections here, you do it in the add-on modules of RFEM, and there you can consider the principle of Saint-Venant, I think. Yeah, should be possible. Yeah.
Okay. There's a question too about wind loads. Would you like to answer it now, or should we leave it for the end?
We leave it for the end, and then at the end
Okay.
we going through all the questions.
All
Good.
right. Okay.
Good. So at the end, I want to maybe I have something for you. I have a quiz for you. So please answer maybe this test for me. Good. Most of you have chosen, so I close this poll here, show you the result. So yeah, most of you were right. A critical load factor specifies which factor can be used to increase the load until the system will collapse. Good. So let's go ahead with the frame. There we do the same. So I change here maybe the nodal force from 400 to 100. And I copy this column here with the help of my favorite function with pair drag and drop. So with press Ctrl key and with a pressed left mouse, I copy it from there to there, 10 meters along the x-axis. Now I have two columns here, but I want to change the height of these columns. So to change maybe the coordinate of the nodes, it's very easy to do that. Just select these nodes, then per right click on node, you can edit the coordinate of the z, yeah, and I put it to 6 meters because I want to have this column 6 meters high. So change it here and automatically the program will set the height of these columns to 6 meters. Then I want to create a girdle here from the left to the right column. So again, I create a new single member. I create a new cross section, in this case an IPE profile should be a height of 300 millimeters. Click on OK. Then I create this beam from the left to the right, and I have my girdle here. Good. Then I make the same thing. Yeah, I calculate everything, and then we watch together the, first of all, the internal forces and also and then the critical load factors. Good. So first of all, we are going to watch the normal forces. I think they are clear. So in both columns, you get a normal compression force of 100 kilonewton. Bending moments, we don't have any bending moments. I think this is also clear because we don't have any horizontal forces and also no shear forces. Good. When I want to see the compression forces, not the compression forces, the nodal supports, I can watch it here by clicking support reactions. I see the vertical forces of the supports. Yeah, good. But this is something not so interesting because I think that's clear. More interesting is maybe the different eigenvectors. So again, here we have 4 different eigenvectors, buckling cases. And when you see, okay, the first eigenvector shows you buckling form, eigenform out of the plane, yeah. And the second also out of the plane, and we have here the critical load factor of 12. So this means we have to multiply this 100 kilonewton by 12 that our system becomes unstable. But in reality, when you have cases like this, it is very, it's not so good because you have form that buckles out of this plane. Yeah, in reality, you have here some supports who would hold this whole thing here in order not to have this buckling form out of the plane. Yeah, and when you watch to a hole, to a 3D hole, you have again additional beams along that side, and then you wouldn't have this eigenforms here. Yeah, so maybe in order to consider that, you can add additional nodal support. So when I put it here, new nodal support, and I want to block the deformation at these nodes out of the plane, I have to create a new nodal support and activate the displacement u-epsilon and then the displacement will be blocked in this direction, and there will be forces, or forces could be happen. So I choose here the nodes, and now watch out, our new buckling cases are new eigenforms. Yeah, and now our first eigenvector is this one, that we have a buckling in this plane. Yeah, and this is also what we know from the structure analysis, from the study, because we calculate or we consider it in a plane, Yeah, so much to the frame. Good. This was our online training. I hope you enjoyed that. And now we have time for answering questions. Praxitelis, what can you tell me?
Okay, then the last question that came in is where to find the project navigator to?
On the left side, you have the project navigator. And when you don't have it here, you find it here at the symbol bar, navigator on, off. When I click on that, you will find the project navigator. And
Okay.
Yeah, the project navigator, exactly.
Okay. Okay, can you throw more light on imperfections considered during second order analysis?
Of course. So look, we have this buckling form here, this eigenvector form, and now you want to bring along this form, along this displacement form, imperfections. This is possible. Use the add-on module RFEM, yeah, and there you can generate your imperfections due to this forms here we calculated in the stability analysis, and then you can calculate it and bring these imperfections. Yeah, use this RFEM generation of imperfections. You find it here also at the add-on modules, RFEM generation of imperfections. This is possible.
Okay, we got the question with the wind loads.
Yeah, with the wind loads, there are different possibilities. First possibility, to make it very simple, you can add here horizontal member loads. So just click here on new member load. Choose the right direction. Choose the right direction here and put here maybe a value of 5 kilonewton per meter, and then put here your line loads, your member loads. This is maybe a very easy wind load, but when you have a more complex 3D hole, something like that, I show it to you. Maybe I open a new program where we have maybe a hole. I hope we have somewhere a hole. No, we don't have any hole. Here we have a hole. And maybe you mean also the wind generator. It's very easily to do that. Here, with the help of the with the tools, we have here the possibility to generate loads very easily. And here we can say from wind loads, and then say, okay, vertical walls or flat roof, something like that. Yeah. And in this case, we have the vertical wall with roof. Then choose the right standard. In this case, I choose here the Eurocode. And then with the help of this bitmap on the right side, you can easily pick up your base geometry. So I do that. I click here, this base geometry, and then also my my roof type and geometry. So I go from there to there to there to there to there, and then and then I have to choose the right load case, and then I can set the wind on which side. So in this case, I want to have this on that side. I can set the height of the structure, also the wind zone, terra category, and so on. Then I say okay, and I have the different wind pressures and so on. Yeah, I can show me also separately like that, and
Okay. Okay, someone is asking if we can show a reinforced concrete beam.
Yeah, of course. I make it here the test example. So it's when you want to do calculations with reinforcement concrete, you have to use one of our add-on modules. So first of all, create the beam, choose a rectangular beam here, put there maybe some coordinates, I don't know, something like that. Choose also the right material. Yeah, this is important. And then create your beam, 10 meters long. Then I need some supports, of course. I put here 2 supports. And then also the loads. Sorry for take some time maybe. Yeah, good. And now you can calculate it. You get your internal forces. And then use the add-on module RF concrete members. When I open this add-on module, you can preset, first of all, your ultimate limit state, so what you want to design and according to which standard. Then also the materials. Here you can change to some settings. Cross sections, supports. I think that's clear. And then here you can consider your reinforcements. Yeah. So what do you want to use as a rebars? Which diameter should they have? And a lot of other stuff. Yeah. So, but it would take a lot of time to do now a single design of a single beam. Okay, but with the help of the add-on module, with concrete members, you can calculate these these beams here. Okay. Next question.
Please throw some light on geometric and material linearity. Someone says.
Can I see the question? Which time?
12:02. Five minutes ago.
Material linearity. Okay, I understand. So as I said before, we calculated these systems first of all here with the different linearities. So the method of analysis. So we have here the geometrical linear analysis and also the second order analysis. So the geometrical linear analysis, what does they do? I make the equilibrium of the whole structure at a undeformed system, yeah. And the second order analysis, or the B delta method, says I make the equilibrium of calculating the forces and the internal result at a deformed structure, yeah. And this was also the point where I showed you the additional bending moment. And when you want to consider different material linearities, just go here on the data navigator, go to materials, create maybe a new material. And here at the material model, you can consider almost every nonlinear materials, whatever you want. You find it also in our handbook. Yeah. And you can also download from GoToWebinar one of our PDFs. There should be the RFEM training manual. I would recommend you to download it from GoToWebinar, but you will get it also by email, no problem. Yeah. Okay. Practicalis, any new questions?
We got many questions that are not that relevant to this training. Do you want to answer all of them? For example, foundation analysis or seismic loads.
Yeah, these are questions referring not really to this training. I would rather answer these questions, which rely more on the general part of RFEM. But horizontal loads, what do we do with? Yeah, maybe you pick up some questions which rely more on that basic training, but we will answer you later. Maybe one more point. I can really recommend you to visit our website. And here, when I change here the language to English, on our website, you find almost everything. I mean, with everything, I mean really everything. So when you have any problems or when you have any questions, don't hesitate to ask us. You can chat with us live. Yeah, you can send us a message. We will answer you immediately. When you have some problems, you can search it here. When you maybe there was a question with with earthquake or something like that, no problem. We have these solutions. When I go here, we have application areas, the dynamic seismic analysis with the help of one of our add-on modules, like the name is ERF Dynam Pro. You can calculate the different vibrations and make also different, now I don't know the word in English, but with the help of our program RF Dynam, when I click on that, you can calculate a lot of concerning loads for the earthquakes, yeah, and a lot of more things. Yeah, I would really recommend you to visit our website. Praxitelis, maybe a question?
Okay, I'm searching. Okay, someone is asking at 12:02 how to correct any identified error during calculation without going back to the model, model the whole structure. Maybe the plausibility check is meant?
I know, yeah. Okay. So you have different options to control your model, yeah. First of all, the plausibility check is possible. The plausibility check says you, okay, if the model was modeled correctly, so it will identify when some members aren't connected to each other, or some nodes are flying somewhere around or something like that. This is possible. And in addition, you have also the possibility to check also the model here with this help. So when you think, so when maybe due to the import and export from other programs to our programs, or otherwise, it can be possible that the data exchange wasn't done correctly or properly. Yeah, here you can identify identical nodes or overlapping members and so on. And for those one who asks for maybe the errors concerning the critical load factors, with the help of this RF stability, you can calculate the different buckling cases, and then you will also see where is the problem of your structure. Yeah, and I have also a very good FAQ concerning unstable system. I have to look it up. Wait a moment, I have it here. And I will post it to the chat. So if someone gets the error with my model is unstable, what could be the reason? I would recommend you this article, this FAQ. I show it to you here. there are different checks to do. I created also this article. So first of all, you have to check your model with different options of model checking. Then also check the stiffening. Can also be some numerical problems, and how can I deflect? How can I detect these causes of instability? I can do it here. Yeah, I can recommend you this article. Good. Praxitelis?
Yes, the recording will be available for everyone. Don't worry about that. Someone asked.
Good. There are so much questions to answer.
Yeah. There are many questions.
So maybe also back to one question at 12.1. Can you check? Yeah, you can do. We will send you some examples of this online training, of course, for sure. Yeah, good.
Maybe we should tell one more time that the add-on modules are available for students.
Yeah, concerning when you have a student version, you have free access to all of these add-on modules. Otherwise, when you want to test it, you can download our trial version, and you have access for 90 days where you can test almost everything. You can download it also from our website. I give you the link for those who doesn't have that. You can get the download free 90-day trial. You can download it from there. I posted in the chat. Good. Yeah, I see one question concerning pushover analysis. It's possible to do that. Yeah. You can here pushover analysis, but it will take us too much time to do that now. But we will send you something. Yeah. Good. Here. How to increase student version license. Just go here to education and request for request for a free student version license. I post also this link, or posted also here to the chat. Here you can request a free student license. And is there any information about new RFEM version? Yes, it is. When you go to update reports or updates and upgrades here at service, you see our newest updates and our newest versions.
What we could also recommend is our new online course. There are 10 or 11 videos on YouTube, step by step how to model a simple structure in RFEM. You can check that out.
Mhm.
There is also shown how you can export the calculation to a PDF. It could be very helpful, I think.
Yeah.
I could post a link in the chat, Daniel.
Yeah, post maybe the link of e-learning. Or I have it here. I have it here. I can
Okay.
post it.
All right.
And yeah, because one of our main efforts is also to increase our e-learning platform, our offer for videos concerning the e-learning. And here I post you the link, and there you have access to our online course, free online course, of course, because it's on YouTube, RFEM for beginners. And there, Praxiteles tell you something about modeling a structure. And you can also watch some recorded webinars. Yeah, good. Yeah, then I would say we will end this now. What would you say, Praxiteles?
Okay, just for the last one that asked, you can simply renew your license if you need it a little bit more for your master thesis. You can renew it under that link that Daniel showed you. Okay, so I would say we can end this.
Okay, so thank you for your attention. And
Thank you very much.
Made it a lot of fun, and we hope we will see us soon together again. And stay healthy at that time.
Yes, thank you very much. We hope you enjoyed it. It was good fun for us. Stay tuned, I would say, for the next part, for part 2.
Yeah, yeah, sign up for the second part of RFEM for students. You will find it here at online training. And here on, yeah, you will find it here at the online trainings. I posted here. Yeah, good.
All right.
But we will send an email again. Good.
Okay, thank you very much.
Bye.
See you next time. Bye.